In the last video, we started talking about inverse kinematics, and I noted some of the assumptions that we have to make in order to do inverse kinematics. Our second assumption was that the second three joints determine the orientation of the end effector. In this video, I'm going to be focusing on this part of inverse kinematics where we deal with the second three joints determining the orientation. Now, there was another relevant assumption that we also made, which is that the second three joints make up a spherical wrist. Here I'm showing a kinematic diagram of this spherical wrist that we talk about in the assumptions. The spherical wrist consists of three revolute joints, with one of the revolute joints having an axis of rotation that is perpendicular to the other two. Now, I want you to notice that the only link length that is labeled in this kinematic diagram is the last one, showing the distance between the wrist and the robot's hand, or its end effector at the end here. The other two links do not have a length labeled on them. The reason why this is because typically these three joints are all located at the same center location. In other words, what you would physically have on your robot is one joint that is capable of all three of these motions. This arrangement of the spherical wrist allows the wrist to rotate to any specified angle. And in this video, I'm going to show you how you will figure out the joint angles theta 4, theta 5, and theta 6 that will put this end effector at any orientation that you want. The first thing that we're going to need to do to accomplish this is to find the rotation matrix that defines the rotation between frame 3 and frame 6. We would call that rotation matrix R36, the rotation of frame 6 relative to frame 3. Let's see if we can derive that matrix now. In order to derive this R36 matrix, we want to start out by recognizing that this matrix is equal to the product of the three matrices that go from one frame to the next. So R36 is equal to R34 times R45 times R56. We can do this because of the principle of linking rotations that we learned about in an earlier video. So to find R36, all we have to do is find each of these individual matrices and multiply them together. In order to do that, we're going to apply some of the things that we've already learned previously. I'm going to take this equation and move it a little bit so we have some room. And let's start out by finding R34. Remember that my rotation matrix has to have one part that accounts for the difference in the orientation of the two axes, and another part that accounts for the joint variable. So the first thing I need to do is figure out how to get frame 3 to match frame 4. And I can see by comparing these two frames that I can achieve that by rotating frame 3 around its own y-axis 90 degrees in the negative y direction. I know that the direction is negative y by applying the right-hand rule. So I'll write down a rotation of negative 90 degrees around y. That will account for the difference in orientation, so the next part that I haven't done yet is to account for the rotation theta 4. Theta 4 is a rotation around either the original z-axis or the new x-axis. I'm going to use the new x-axis because it's easier for me to think about rotating around relative axes rather than around absolute axes. So I'm going to post-multiply a rotation of theta 4 degrees around the new x-axis. And that gives me my R34. Right away, I'm going to go ahead and plug in the values for these two matrices. I'll start out by going and getting the matrix for rotation around y and plugging in -90 degrees to that. So I'll go back to my three rotation matrices shown here, and I'll grab the rotation around y matrix and plug in -90 for these values. And I'm going to skip a step here and calculate out what the value of the cosines and the sines of -90 are. So I've done that here, and I wrote out the matrix for a rotation of -90 degrees around y. Now I'm going to also write in the matrix for a rotation of theta 4 degrees around x. So I'll go back and get the x matrix and plug in theta 4. I've plugged in theta 4 here for the rotation around x matrix, and I'm now going to multiply these two matrices together. After multiplying these two matrices, the result that I get is shown here. And that's my answer for R34. The next thing I'm going to do is find the matrix for R45. And I'm going to do that in the same way. In the interest of time, I'm going to go into less detail here. So R45 will be equal to a rotation of 90 degrees around y, followed by a rotation of theta 5 degrees around the negative x-axis. So I'm going to say around x, and I'll make this a negative theta 5. So I'm going to go ahead and do the multiplication of these two rotation matrices, and I'll show you what the result is. So here now I've plugged in my rotation of 90 degrees around y and a rotation of negative, I should have a negative sign here, negative theta 5 degrees around x. So now I've found R34 and R45. The last thing I'm going to do is find the matrix R56. So I'll scroll back up here to take a look at my 5, 6 origins or frames, and I see that 5 and 6 are already in the same orientation, so the only part of the rotation matrix I have to account for is a rotation of theta 6 degrees around z. So the rotation matrix 5, 6 will be really easy to write. I'll just get the rotation around z matrix and plug in theta 5, or theta 6 rather. Now that I've found R56, R45, and R34, I'm going to multiply them together to get R36. So here I've written down all three of the matrices that I need to multiply together in order to get R36. Multiplying these matrices together is going to be a bit of a pain, but once I do it, I can use the equations that I get over and over again. I don't need to rederive this equation every time I have a new manipulator. As long as it has a spherical wrist, I can use these equations again. Here I've multiplied out these matrices for you and I've shown you the result. I also made a simplification just to make it look a bit less messy, in that I dropped all of the theta symbols. So all of these 4s and 5s and 6s, they all mean theta 4, negative theta 5, and theta 6. So this is the rotation matrix that we come up with for the rotation from frame 3 to frame 6. So how can we use this matrix to figure out what the values of theta 4, theta 5, and theta 6 should be? The way that we do that is by specifying what we want the values of each of these elements in R36 to be. For example, let's suppose that we want our end effector to be positioned in such a way that it has a rotation of 90 degrees around its own z-axis, or rather 90 degrees around the original z-axis. Let me go back up here to this diagram so I can show you. Let's imagine that this end effector is holding a spray paint can. And let's suppose we want the spray paint can to be pointed into the screen in order to paint the object. In order to point this spray paint can into the screen, we need the end effector to be rotated 90 degrees around this axis right here, y3. So we're going to write the values of a matrix that represents a 90-degree rotation around the original y-axis. So what we do is we go back and look at our rotation matrix, and we get the y rotation matrix and we plug in 90 degrees. So I'm going to write it like this. I'm going to say let R36 equal a rotation of 90 degrees around y. Then R36 will be equal to the cosine of 90, 0, negative sine 90. Here I'm just plugging in 90 degrees to my y rotation matrix. Sine 90, 0, cosine 90. I'm going to calculate this out so I know what each of those numbers is. So that gives me a desired rotation matrix 3, 6 of 0, 0, negative 1, 0, 1, 0, 1, 0, 0. Now, I know what I want the R36 matrix to be, and I have an expression in terms of theta 5, theta 6, and theta 4 for each of the elements of the rotation matrix. I can figure out values for theta 4, theta 5, and theta 6 by setting the elements of this matrix equal to the elements that I want the matrix to be. I'll start doing that by using the most simple elements of this matrix. So I'm going to start out with this cosine theta 5 in the lower right hand corner. I know that I want that lower right hand element to be equal to 0, so I can write the very simple equation that the cosine of negative theta 5 is equal to 0. That allows me to solve for theta 5, which in this case is 90 degrees. Now that I know the value of theta 5, I can substitute theta 5 into the other elements of this matrix to find the values of other thetas. For example, I might take this element right here. I'm going to plug in 90 degrees for theta 5, which will simplify this expression. Since the sine of negative 90 is negative 1, this expression becomes the cosine of theta 4. And I can set that element equal to this element, because they're in the same place, and write the expression negative cosine of theta 4 is equal to 0. And that gives me theta 4 equal also to 90 degrees. Now that I know theta 4 and theta 5, I can do the same process to figure out what theta 6 should be. Now, note that there are 9 elements of this matrix, but there are only 3 variables that we're trying to figure out. There's kind of a standard process to help me figure out which ones of these matrix elements I should use to calculate theta 4, theta 5, and theta 6. In the next video, I'm going to be giving you a simple step-by-step procedure that we can use to do inverse kinematics for rotation in the case where we have a spherical wrist like this one, so that you don't have to rederive this matrix every time. You can just apply a few of these expressions that we've found to get your end effector into any orientation that you might want.